We used this diagram to interpret the relationship between the energies of the sublevels and the ionization energy of 3-second period elements. We can use the same diagram to consider the electron affinity, which we take from figure 3.8 in the textbook. Electron affinity measures the energy change when an electron is added to an atom. So rather than identifying an electron in the diagram, we need to identify the open spots or holes in the sublevels to where an electron can be added. Those are shown by the yellow circles. Again, imagine that you are standing at the top, this time with extra electrons to throw down into the atoms. An electron would go into 2s on lithium, and the open spots in the 2p on carbon and fluorine. Now, if you only had one electron, which atom would it want to go to? It would prefer to go to fluorine since, based on our second pillar of chemistry, systems in nature seek the lowest energy they can find. Fluorine would have the greatest affinity or attraction for an electron. More technically, the energy change the electron experiences is greatest when it goes into fluorine, and least when it goes into lithium. So fluorine has the largest electron affinity, and lithium has the smallest electron affinity of these three atoms. The textbook actually uses figure 3.8 to explain electronegativities, which are given the symbol chi and shown for these three elements. I would argue this is a bit misleading since for elements in the p block, all of the valence electrons, in this case 2s and 2p, can be involved in bonding. Therefore, the energies of the 2s electrons can also affect electronegativity. However, that's a minor technicality, and the trends we observe in electronegativity certainly correlate with the energies shown in the figure.